Alright, this video will cover Chapter 3, Section 4, and our topic is properties of logarithmic functions. What you'll learn about, we're going to learn about properties of logarithms. We're going to take a look at change of base. We're going to discuss graphs of logarithmic functions with base b, and we are not going to talk about re-expressing data. And why? The applications of logarithms are based on their many special properties, so learn them well. So here are some properties of logarithms that are very useful. Let b, r, and s be positive real numbers with b not equal to 1 and c be any real number. We have a product rule that says log base b of the product rs is equal to log base b of r plus log base b of s. We have a quotient rule that says log base b of the quotient r over s equals log base b of r minus log base b of s. And we have a power rule that says log base b of r to the c power is equal to c times log base b of r. Again, these are very useful rules when we are working with logarithmic equations and trying to solve them. So here's a proof of the product rule. So if you were asked to prove that log base b of the product rs equals log base b of r plus log base b of s, could you prove that? And I'll give you a second to think about that. So pause the video, think about how you would go about establishing that, and then play the video and we'll take a look at this. So if we were to let x equal log base b of r and let y equal log base b of s, the corresponding exponential statements are b to the x equals r and b to the y equals s. Therefore, rs, the product rs, would equal b to the x times b to the y, which we can simplify that using an exponent rule. Rs would equal b to the x plus y. Okay, same base, add their exponents. So if we take the log of both sides, log base b, we have log base b of rs equals x plus y. Well, we defined x and y to be log base b of r and log base b of s. So log base b of the product rs would equal log base b of r plus log base b of s. So here's an example. Assuming x is positive, use properties of logarithms to write log of the product 3x to the fifth as a sum of logarithms or multiple logarithms. And so we call this expansion. One of the things that we will do with these expressions is we will expand them out. So here's what this would look like. We have our product, the log of our product. So we can use the product rule here to write log of 3 plus log of x to the fifth. And then we can take x to the fifth and use our power rule to bring the 5 out in front of the log of x. So this is what this would look like in expanded form. Now, here we are condensing, okay, or simplifying, I guess. Assuming x is positive, write 3 times ln of x minus ln of 2 as a single logarithm. So sometimes we might have to expand an expression out, sometimes we might have to condense it down and write it as a single logarithm. So 3 ln of x, we could write that as ln x to the third minus ln of 2. Since we have a subtraction here, this is a quotient rule problem, so we can write ln of the quotient x cubed over 2. Sometimes in order to work with equations, we have to use what's called a change of base formula. This comes in handy many times, and sometimes it's the one that we forget, but this is a very simple rule, but it's a very powerful rule. So for positive real numbers a, b, and x with a not equal to 1 and b not equal to 1, we say that log base b of x equals the quotient of log base a of x over log base a of b. Okay, so what we can do is we can take this log that we have and we can rewrite it with an expression of log of whatever base we need, whatever is useful for us. Okay, so here's an example of the change of base. We want to evaluate log base 3 of 10. And the thing that you'll notice about your calculators Our calculators have a log button and they have a natural log button, meaning we can do a common logarithm and we can do a natural logarithm on our calculators, but we can't do log base 3. We can only do log base 10, log base e. So what we have to use is we have to use a change of base formula to do this. So what we do is, using the change of base formula, we're going to rewrite this as a quotient of two common logarithms. So the numerator would be the common log of 10, and the denominator would be the common log of 3. So log 10 divided by log 3. Well, log 10 is 1. So then we just need to use our calculator to divide 1 divided by log 3, and we get approximately 2.096. So log base 3 of 10 is approximately 2.096, but we need to use our change of base formula to come up with that value. So here we can look at some transformations of logarithmic graphs. Again, what we need to understand is we may have to use a product rule, quotient rule, or a power rule to help us maybe possibly rewrite the function first to then talk about what happens to the graph, the transformation of the graph. Here we have functions g of x is ln of x squared, h of x is log x, and k of x is natural log of 3x. And so we want to see what happens to the graph of f to get these three functions. So if you want to, I pause the video right now. Think about what each one of these graphs is going to look like based off of f. What's the transformation that's done to f to get g, h, and k? So here's what g is going to look like. Since ln of x squared equals 2 ln of x, the graph of g of x is obtained by vertically stretching the graph of f of x by a factor of 2. And again, we use our power rule to rewrite g. So here if we look at h of x and how h of x is a transformation of f of x, since log x equals natural log of x over natural log of 10, the graph h of x is obtained by vertically shrinking the graph of f of x by a factor of 1 over natural log of 10, which is approximately 0.43. And again, what we would be using here is a change of base. And again, the reason why we're doing the change of base is just to compare log x to ln of x and discuss its transformation. We know what the graph of log x looks like, but we can't really compare it to ln of x without doing this analysis right here. So k of x is ln of 3x. So ln of 3x is natural log of 3 plus the natural log of x. So the graph of k of x is obtained by translating the graph of f of x up natural log of 3 units, or 1.1 units. So there we use our product rule to rewrite k to then be able to take a look at what happens to f to get k. So there we have vertical translation.